Hey, welcome back, students. Hey, what we want to go ahead and do today is we want to go ahead and review a little bit of the gas laws. And so if we go ahead and look at this, we're going to go ahead and begin with the first law. Now, we've already explored Boyle's law, and what we learned from Boyle's law is that it follows the following equation. We know that it involves pressure and it involves volume. And so according to Boyle's law, we're going to see that the pressure and the volume are inversely proportional. And what this means is that as the pressure increases, the volume is going to decrease. And if the volume increases, pressure will also decrease. And so this equation is very important to us, especially when we only have two variables. So this equation is often used to solve those kinds of problems that only have variables that include pressure and volume. And when you're looking at solving these types of problems, what you want to do is look for keywords such as initial pressure or initial volume. Essentially, that's going to be your P1 and your V1. And the other item is look for words like resultant or final volume or pressure, because that's going to be your V2 or your P2. A second equation that we looked at before was Charles' law. And so this equation here is going to be written as follows. You're going to get the volume divided by the temperature in the first instance, and V2 divided by T2 in the second instance. Now, according to Charles' law, the volume and the temperature are proportional to one another directly. And so what this means is if you increase temperature, that means that the volume is going to increase. And if the volume increases, that means that the temperature must have increased, because if we remember what we learned about the kinetic molecular theory, we learned that molecules are going to be moving pretty fast, especially if you increase its temperature. And as a result of moving so fast, they're going to create more collisions with the barrier of whatever surface or container they're in, causing the volume to increase. If we have this particular equation in our possession, what we're trying to figure out here is when we're trying to solve problems, we're going to be using this equation, V1 divided by T1 equals V2 divided by T2, especially when we're dealing with equations or problems that have only two variables, temperature and volume. And again, like the other one, Boyle's law, we want to look for keywords such as initial temperature or volume, or resultant temperature and resultant volume. The next equation that we're going to go ahead and look at is going to be Gay-Lussac's law. And in this particular law, what we've got here is we've got a equation that involves two variables, pressure and temperature, and it looks like this. Pressure divided by temperature is going to be equal to constant K. Now, this constant is something that we calculate ourselves. And so we calculate it by taking the pressure and dividing it by the temperature. Now, according to the Gay-Lussac's law, we know that pressure and temperature are going to be directly proportional. Again, like the previous equations, particularly Charles' law, if we increase the temperature, this is also going to cause an increase in the pressure. And vice versa. So if we have an increase in pressure, this will be a direct result because the temperature increased. Now, this equation is going to be used when you're trying to solve problems that only contain one pressure variable and one temperature variable. And typically what we're going to try to do is try to solve a constant. So maybe I ask you, if you have this pressure and you have this temperature, what would be the constant for this equation, according to Gay-Lussac? Okay, and so this constant then is something that we solve for, and we figure this out by dividing the pressure divided by the temperature. Now, another new equation that we're going to be looking at today is going to be Avogadro's law. Now, Avogadro's law essentially deals with volume and number of moles. Now, we recall from previous discussions, Avogadro was very instrumental in allowing us to understand that 1 mole of a substance contained a certain number of particles, and that was 6.02 times 10 to the 23rd. And so here's the actual equation that we're going to use. It's the very top corner. And according to Avogadro, the law essentially proposes the following, that the number of moles of a gas is directly proportional to its volume. In other words, as the number of moles of a gas increases, so is the volume, simply because you have more particles available. And that makes sense. It's kind of like taking a room, for example, and the more people you put into the room, so assuming you can bend the walls of this room, if I put in a certain amount of people and I fill up the room, then we're at capacity, it's full. But if I continue to add more and more and more, essentially it's going to start stretching the walls. Kind of like what happens when you overstuff a suitcase. you can't really close it down because if you've got clothes overflowing on the edges. Well, it works the same way here with the molecules in the gas. Now, the equation is used to solve problems that have variables of volume and moles. Now, keep in mind that moles is identified as a N in the equation, so we're looking at N as the number of moles. And we also want to make sure that when you're solving these types of problems, you're looking at keywords such as initial moles or volume or resultant moles in volume. Okay. Now, these are the actual four equations that we have, and we're going to use these four equations to go ahead and derive the another equation that we call the combined gas law. And the combined gas law is going to be derived essentially by taking the Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law and combining them all together. Let me take a couple of more slides here and I'm going to show you how we actually do that. Well, the first step we take is we take Boyle's law and Charles' law. So here's Boyle's law, here's Charles' law, and we're only going to take a look at the left side of the equation. Now, that doesn't mean that we're going to abandon the right side. It just means that we're just, for the purpose of demonstration, I'm just going to look at the left side. But you're going to be doing the same exact thing to the right side. So the next thing that we're going to do is we're going to look at this right side and we're going to multiply both of these sides. So we're going to take the P1, V1, and we're going to bring it down here. And then we're going to take the V1, T1 of Charles' law on the left-hand side, and we're going to bring it down, and we're going to multiply these two together. Now, we're going to do the same exact thing to the right side of the equation. So we're going to take the P2, V2, and we're going to bring it over, and we're going to take the V2 divided by T2 and bring it down. And when we do, that's going to give us the same number. Now, I know I just wrote here V1 divided by T1, but that just goes to show that we have the same number because both of these things are equal to one another, okay? And so that's essentially what we've got here. So what we're going to do is we're going to focus on the left-hand side. And if we look at this side, if we multiply these two together, we're going to do the following. We're going to go ahead and use distributive property to find out what the products are going to be. And when we do this, we're going to get on the numerator P1 times V1 times V1 divided by T1. Okay. Notice that we multiply the numerator separately from the denominator, so we divide across in the numerator and then divide across in the denominator, and that's how we get these two. When we go ahead and factor these a little bit further, multiply it all, we're going to get P1 times V1 squared divided by T1. Since the V1 is multiplied by itself, what we wind up getting here is a squared number over here. Now, we take this section that we've already done, now we're going to introduce Gay-Lussac's law. And when we introduce Gay-Lussac's law, we're going to essentially multiply it as well. And again, we're going to use distributive property to do this. And so we're going to get P1 times V1 squared times P1 in the numerator. And then we're going to get T1 times T1 in the denominator. And so this is what we've got here. When we actually multiply it all the way out, we wind up getting P1 squared times V1 squared divided by T1 squared. Notice the one thing that they all have in common are squares. Each of these are squares. And so we want to go ahead and simplify. Same thing that you do in mathematics, we're going to go and do that here. We're going to simplify this product that we've got here. And so the way we do that is we're going to go ahead and take the square root. So if we take the square root of this number, what that is going to do is that's going to give us a situation where we're going to be canceling not only the square root, but we're also going to be canceling the powers or the squares. And so those go ahead and cancel as well, leaving us nothing but P1 times V1 divided by T1. Now, this is only half of the full equation. Remember that. We still need to do the same thing to the other side. And when we do, we get the following. Okay, so notice the left-hand side is P1 times V1 divided by T1, and this is going to be equal to P2 times V2 divided by T2. And so this is what we call the combined gas law, at least the one we consider to be final in class. Okay, and so here's the equation. It's important that you go ahead and write this down. It's very important. So now, the one thing we look at this, though, although this is something that's often talked about in classes across many chemistry classrooms, one of the things that they really don't talk about is they never incorporate Avogadro into this equation. But we're not going to do that. We're not going to ignore it. We are actually going to include Avogadros because we still need to do this in order to get the full version of the combined gas law. Now, technically, this is the combined gas law, but it lacks Avogadro. So Avogadro's law stated at the very beginning that volume is proportional to the number of moles. And so because of that, we have to include moles, which we're going to represent as a letter N, into the equation that we just derived. Okay, so we're going to take this combined gas law and then we're going to incorporate Avogadro. And if we do, we're going to incorporate Avogadro in the following positions, in the denominator on both sides. Now, this is what the combined gas law should look like, okay, when we have pressure, volume, temperature, and number of moles. Now, for the sake of doing this, we really need to come back a little bit just for a second and talk about what we talked about when we started this chapter, which was that gases normally are not ideal. They don't really behave in any certain way, except how gases behave. But sometimes they do have these ways of behaving that comes very close to behaving in an ideal fashion. But when we talked about this ideal, we need to really talk about what the conditions are. And so these ideal conditions that allows a gas to behave in an ideal way are the following. And that means that when we talk about the pressure, what we're really referring to is we're talking about 1 atmosphere of pressure. When we talk about temperature, we're really referring to 273 Kelvin, which is the absolute, or rather the standard temperature. And when we're talking about volume under these ideal conditions, we're talking about 22.4 liters. And the number of moles involved are going to be 1 moles. And so if I can go in here and let's look at on the right hand side of the equation, since P is equal to 1 atmosphere, T is equal to 273 Kelvin, volume is equal to 22.4 liters, and N is equal to 1 mole. What if I were to come in here and replace P2, V2, T2, and N2 with these values? And in fact, that's what we're going to do. So let's go ahead and replace these values into this area, and we've got them here. And once we do this, we see that we've got now have a numerator and a denominator. And so let me simplify this and remove this and clean it up a bit for us. So let's put this here. And notice, once we substitute the values, we get the following equation on the top. And so we're going to go ahead and multiply across and multiply these two numbers. So if I take 1 atmosphere multiplied by 22.4 liters, what I get in the numerator in the second equation is 24.4 atmosphere liters. And if I take the denominator of the first equation on the top here, 273 times 1 mole, what we're going to wind up getting is 273 Kelvin mole. Simplifying this a little bit further, if I take these two numbers now, 22.4 atmosphere liters, divide that by 273 Kelvin mole, what we wind up getting is this number here, 0.0821. Notice the units. The units of this particular number that we've derived is atmosphere liters per Kelvin mole. Now, this 0.0821 has a special name. It's actually a constant. And this constant is what we call R. And this R is what we call the ideal gas constant. And it can be used to solve a lot of problems using the ideal gas law. In fact, we're almost there. This actually, for all intents and purposes, is the ideal gas law. But you probably have seen the ideal gas law written slightly different. And so let me show you what that looks like here. We're going to take the R, we're going to replace 0.0821 with this R. And so I'm going to go ahead and put it in here in this equation, and here it is. So I'm going to take this R, replace it right here in the middle, and this now begins to look like the ideal gas law that you are probably familiar with, especially if you read the chapter. And so let's go ahead and clean it up a little bit without the numbers, and this here is the ideal gas law. So you can see that we can take Boyle's, Charles, Gay-Lussac, Avogadro, and we can come up with not only a combined gas law, but we can also come up with the ideal gas law. And this ideal gas law will help us identify any problem that we have using gases. Assuming we've got very close to ideal conditions, we can use this law and make it work for us. Okay? So we just learned about the equations. Now in the next video, what you want to do is you want to go ahead and put this knowledge to the test and see if you can identify the actual equation for the test for the various sample problems that I've already prepared for you. So take a look at that video and we'll talk to you soon.